Thank you. There we go. Got it. Can you see my screen because the recording stopped that?
We can see the screen.
Okay, good. Okay, yeah, thanks for inviting me to speak here today. So yeah, I was asked to give kind of an overview of some recent results in the simulation of black hole neutron star and neutron star binaries with the spec code. And so naturally, what I'm going to discuss today covers a range of projects by different people in the SXS collaboration, and not just my own work. I'm going to mostly cover two different broad areas here. I want to discuss some recent improvement to the algorithm, the physical realism of the spec simulations, and then also give you some idea of results that we actually get by performing simulations with these new methods. And specifically, I'm going to talk about three main projects. One, I'll discuss the implementation of Monte Carlo radiation transport for the treatment of neutrinos in the spec code and how we are using them in neutron star merger simulations so far. Second, I'm going to talk a little bit about the impact of heating from our process nucleosynthesis on the evolution of the matter outflows on timescales longer than most merger simulations, more like seconds long timescale. And how that extra heat deposited in the outflow might impact their properties. And finally, I'll talk a little bit about long axisymmetric simulations of post-merger remnants, including physics that we usually do not include in mergers and post-merger simulations, such as, for example, diffusion of entropy and viscosity, diffusion of entropy and composition in the post-merger remnant, as well as the impact of the choice of low-density nuclear physics that you make, the equations of state, in these post-merger simulations. Before getting into any of that, I want to briefly remind you of the specifics of the spec code, how it works, and what it can currently do. So spec is a little bit different from most of the code currently used in numerical relativity for neutron star mergers in that it uses two separate grids, one spectral grid for the evolution of Einstein's equation and one either finite volume or finite difference grid for the evolution of the fluid and possibly magnetic fields and neutrinos. And each of those grids is fairly adaptive with the spectral grids shown, for example, here on the left, having all of those differently shaped subdomains that adapt to the geometry of the system. And on the right, the finite volume grid use fairly standard methods in the numerical relativity community with those nested grid with about a factor of 2 resolution improvement between different levels. One advantage in spec is that because we do not evolve Einstein's equation, we can basically ignore on the finite volume grid here any region where there is no matter. So that leaves you with these weirdly shaped grids here that only cover the region with some matter included. And that changes adaptively over the course of the evolution as matter moves through the grid. But otherwise, our finite volume grid is fairly close to what the standard methods are in the simulation of neutron star mergers, with the one exception in this regime being, of course, the particle-based code that Stefan Rosswag will talk about in the next talk. In terms of the physics included in the simulations, there is some implementation of magnetohydrodynamics in spec. Also, this is definitely not the specialty of Foucart. For example, we only have, at least for the grids that we use for mergers, the ability to use divergence cleaning and not constraint transport for maintaining the constraint that divergence B is equal to 0. But none of the simulations that I'm going to talk about here actually involve magnetic fields. Our recent focus has mostly been on the impact on various equations of state and various algorithms for neutrino transport in these simulations. And so spec is capable of handling a fairly wide range of equations of state, analytical or tabulated, and has multiple neutrino transport scheme included, which would be a large part of what I'm going to discuss in the next section. Additionally, in recent months, we have started implementing some other non-ideal effects in the fluids, such as subgrid viscosity and diffusion of composition and entropy, which will be particularly useful for the long-term evolution of post-merger remnant, as we will see in the second part of this talk. And finally, we have modified the spec code so that most of these algorithms can be used in both 3D, which is standard method for mergers, as well as in axis symmetry, which can be useful for faster post-merger evolutions. The exception at this point being the Monte Carlo radiation transport code, which we are currently porting to 2D, but haven't fully tested in that regime. All right. So the first, part of the algorithm that I would like to touch on in this talk is a neutrino transport. We know that neutrino transport is very important for example, determining the composition of the outflows in merger simulations, and also as the main source of cooling in the post-merger remnant. That means that neutrino-matter interactions, neutrino transport, is going to be crucial for determining the outcome of nucleosynthesis in the matter ejected by mergers, because that's very sensitive to the composition of the outflows, as well as consequently the properties of kilonovae, the optical infrared transient powered by these outflows. But solving the equations of radiation transport is a relatively costly problem. In theory, we would like to at least solve Boltzmann's equations for the distribution function of neutrinos, which means evolving a 6-dimensional function in time, because the distribution function is a function of not only the position of the neutrinos, but also the energy and direction of propagation. And we have to do this for each neutrino species and each anti-neutrino species. So electron, tau, and mu neutrinos and anti-neutrinos. In addition, there is some non-trivial coupling between different parts of the parameter space. For example, very different momenta in the distribution function can be coupled through scattering events. Then you can have a process such as pair annihilation or other pair processes, as well as oscillations of neutrinos into different species, which complicate your problem. So at this point in merger simulations, we do not include oscillations at all, only in post-processing. But maybe the most difficult coupling to treat, as we will see in the rest of this discussion, is there's a very stiff coupling between the neutrinos and the properties of the fluid, specifically the temperature and composition of the fluid, at least in the densest and hottest region of your system. And if those stiff coupling are not treated properly, for example, using implicit time-stepping methods, you can easily get numerical instabilities in your evolution and very unphysical evolution of your fluid and possibly your neutrino distribution function as well. But again, all together, this is a fairly complex problem to do properly, this Boltzmann transport. And so most simulations to date have used some sort of approximate treatment of the neutrinos. The most common being probably the leakage scheme, which is a kind of quasi-local method which allows you to determine from the local properties of the fluid and an estimate of the optical depth, how much energy leaves a given grid cell due to neutron emission and how the composition changes due to that emission. But is, at least in the methods currently implemented in merger simulations, not capable of easily predict if a neutrino is emitted at one point and then reabsorbed at another point, which is very important for the evolution of the composition of the outflows. There are ways to actually include reabsorption leakage scheme, but it typically depends on knowing the geometry of the system and has not been done so far in the short merger simulations in GR. One step further than leakage is to go through the moment scheme, which I'll discuss in a minute, but which actually evolves things like the energy density and momentum density of the neutrinos. But we'll see that even that is evolving an approximation to Boltzmann's equation of radiation transport. And so in recent years, there has been a bit of a push towards actually evolving Boltzmann's equation of radiation transport with the methods that have been successful in evolution so far being mostly Monte Carlo algorithms, which have been used by the Los Alamos group for post-merger simulations and by our own collaboration for binary neutron cell merger. But I should say there are other ways to do a full Boltzmann transport that are currently being investigated and that I believe will probably be successful as well in the next few years and might in the long term actually be more efficient than Monte Carlo method, as we will see. So to understand why we actually wanted to go to Monte Carlo radiation transport, it's worth taking a step back and looking at the moment formalism and what its strengths are, what we have learned from using moment transport, but also where the moment formalism actually is lacking and causing some significant errors in our predictions. The general idea behind a moment scheme is that you integrate Boltzmann's equations of radiation transport over momentum space with different different powers of the neutrino momenta used to weight your integral. And so that gives you, without any weighting, an evolution equation for the energy density of neutrinos, the zeroth moment of the distribution function, with one power of the momentum, an evolution equation for the momentum density of neutrinos, and so on, the pressure tensor being the second moment, and so on. Now, this is very convenient in merger simulations because the equations that you end up with for these moments are very similar to the fluid equations. In fact, it's basically the same method as what is used to derive the fluid equations. And so you can reuse a lot of the methods that you have developed for the evolution of the fluid with conservative schemes. The difficulty now is that in a fluid, we do need to close the fluid equations by providing an equation of state. The pressure as a function of density, temperature, composition, typically in mergers. But in a fluid, that can be done if you know the microscopic interactions between particles by assuming a statistical equilibrium between all of the particles forming the fluid. That's the definition of a fluid. But for neutrinos, we can't do that because in some regions, neutrinos are not in statistical equilibrium. They might be free streaming or partially coupled to the fluid. And in those regions, we do not know what the pressure of the neutrinos, for example, is. And so we actually need to use an approximation for that closure relation, which we know is going to lead to the evolution of an equation that is slightly different from Boltzmann's equations of radiation transport. And the consequence of that is that as you increase the resolution of your simulation, you are converging to a solution that is not a solution to the true Boltzmann's equations. You are converging to a solution of that approximate problem that you are solving. And so you do not have a simple way to estimate your errors when using moment scheme because you are not converging to the correct solution. Another important limitation of these moment schemes as implemented for merger simulation is that we typically integrate over the energy of the neutrinos in merger simulations. And so we have to make a choice for the energy spectrum of the neutrinos, which is also very important because neutrino-matter interactions are very strongly dependent on the energy of neutrinos. And so a bad choice for that energy spectrum is going to lead to very large errors in neutrino-matter interactions. And that is not an intrinsic limitation of moment scheme. You can make an energy-dependent moment scheme. But in my opinion, this is actually probably more expensive than going to something like Monte Carlo. And I'm happy to discuss that later if anyone is interested. On a more technical note, there is also a difficulty in implementing moment scheme in treatment, again, of those dense regions where you need either a hybrid leakage moment scheme, as was originally implemented by Yoshiro Sekiguchi in the first moment simulations, or some sort of implicit time stepping in these regions, which makes your evolutions a bit more expensive, which is what we started doing in the spec code. And more recently has been greatly improved in paper last year by David Radice and collaborators, which is probably the state of the art right now in implicit time stepping for these moment schemes. Now, from the very first simulation using moments, people have shown that reabsorption of neutrinos in the outflows is actually very important and is going to significantly impact nucleosynthesis in these outflows. This was shown in this manuscript by Wanajo and collaborators based on the simulations by Yoshiro Sekiguchi, where you can see here on the left, for example, the composition, the electron fraction of the outflows for a range of simulations using moment scheme. And you see that there is a pretty broad range of electron fraction from about 10% protons to about 45% protons, the proton fraction being the same as the electron fraction in these systems. While if you did not include transport of neutrinos or did not include neutrinos at all, you would find a much narrower range with much more neutron-rich outflows. So you would only produce a lower YE outflows here. And that has also an impact on nucleosynthesis. Again, this is the abundance of various elements produced by these outflows as a function of mass number. And you can see the simulation produce this red curve here for reference. Solar are process abundances or inferred abundances, at least, are the black dots here. You can see that you produce a very broad range of nuclei if you have this broad range of electron fraction. But if you did not include transport and did not have these higher YE outflows, you would not produce these lower mass elements here, and thus have very different nucleosynthesis results. This also has a significant impact on the properties of kilonovae, because which elements are present in these outflows can very significantly change the luminosity, color, and duration of kilonovae. Okay. So quantitatively, we have learned a lot actually from these moment simulations. To make quantitative predictions, we would need to know, how accurate are these moment simulations. And as I mentioned, there are two important sources of errors in these moment scheme. One has to do with the closure for the pressure tensor for the two moment scheme that are typically used today. And one has to do with the closure chosen for the energy spectrum of the neutrinos. The kind of error you get from the closure on the pressure tensor is shown on the left here. The two simulations that I'm showing you here are just two beams of neutrinos coming from the bottom, which would normally cross each other. The simulation on the right use the correct closure taken from a Monte Carlo simulation, while the simulation on the left use the most standard closure for merger simulations today, the Minerva closure. And you can see that in that case, the two beams of neutrino collide and merge in an unphysical shock. And so this is clearly erroneous. In my view, this is not the most important source of error in these simulations because this mostly happen in low-density polar regions, a little bit farther away from the remnant that where most neutrino-matter interactions happen. This might be very important if you care about the energy deposited by pair annihilation in polar regions, for example, which will be impacted by these errors. But if you care about the composition of the outflows, I think this is actually a subdominant source of error because it does not happen in the regions where most neutrino-matter interactions occur. A much more important problem is that energy closure. And the impact of that choice of neutrino energy is shown on the right plot here. This is something we did in 2017 using two different choices for that energy closure that were both reasonable within the information that we have at our disposal in these moments simulations. The two simulations are the solid curve and the dash curve. And then the blue curve shows you the composition of the outflows in the equatorial plane, which, as you see, is not strongly impacted by neutrino-matter interactions. And that's not a surprise. We know that there aren't many neutrinos there. So the outflows remain quite neutron-rich and do not really change much whatever you do with your neutrinos. But for the polar outflows, which are significantly impacted by neutrino-matter interactions, you see that there are very significant difference in the electron fraction of the outflows, depending on which energy closure you choose, by about difference of about 0.15 here in YE, which is huge if you are trying to predict the outcome of nucleosynthesis in these outflows. So this is kind of a worst case scenario in that because we do not have magnetic fields in these simulations, the late time outflows that we have are probably slower than in a real, than in a physical system. And so they actually interact more with neutrinos than they would otherwise, which probably increase the difference here. But it gives you an idea of the kind of error that we might make by using a moment scheme. So that was, for me, the main motivation of going to something that is called a full Boltzmann transport, because actually going to an energy-dependent M1 scheme, significantly increase the cost of using the moment formalism. Basically, you multiply the cost by the number of energy bins that you are using in your system. That can very quickly become prohibitive. While in contrast, using Monte Carlo algorithms to do full transport is actually not that expensive in these simulations as we will see. The idea behind the Monte Carlo formalism here is that we are going to sample the distribution function of neutrinos by using superparticles or packets, which each present a large number of neutrinos. And that sampling occurs at the emission step of the packets where you sample the spectrum of emission of the neutrinos in the fluid frame. And then those packets are individually transported along geodesics and have a probability to scatter or absorb. That depends on the absorption capacity and scattering capacities provided by nuclear physics tables. And they basically propagate as individual neutrinos do. So it's very easy, conceptually at least, to understand what these packets are doing. But this is a very efficient method if you are trying to do a relatively low resolution simulation in a high dimensional space. And that's because the Monte Carlo method is very good at placing computational resources right where you need them. This is illustrated by the figure here. This shows you a vertical slice through a neutron-star merger. And red dashed lines here are density contours. So this is the surface of the neutron star, roughly. And then here you have high density contours in the disk, and then a lower density contour within the disk as well. And then the polar regions are largely devoid of matter. And the colors shows you the logarithm of the number density of packets in the simulation. And you can see that the vast majority of the packets are focused right on the hot surface of the neutron star, or here in this shocked region in the accretion disk, with some packets also in these regions here where there is significant neutrino-matter interactions, and nearly no packets in the farther away regions here when there is no neutrino-matter interactions or negligible neutrino-matter interactions. And this is the case for all three species of neutrinos included in your simulation, which are the three plots that you can see here. So these are very efficiently use your computational resources for a problem that's very inhomogeneous, where most of the neutrinos are in very narrow region of parameter space, and you need to resolve that efficiently. And so if you wanted to implement Monte Carlo methods in your own code, what difficulties can you expect? Well, the first one, which is kind of more bookkeeping than fundamental, is to properly parallelize your new code. That's the difficulty because clearly, as you can see from the previous plot, the neutrinos are distributed very differently from the fluid. If you just assign neutrinos to the processor evolving the relevant fluid cell without doing any extra work, you would have a very unbalanced evolution. So you need to either rebalance your entire evolution, neutrinos plus fluid, according to the cost of the joint evolution of both sectors, or you need to parallelize your neutrinos separately from your fluid evolution, which is what we do in spec. I think both are properly valid. One thing to keep in mind, though, is that the distribution of neutrinos can change a lot over the course of a simulation. And so if you do parallelize the neutrinos and the fluid together, you are going to have to regularly reorganize your distribution of fluid cells across processes. So that's more of a bookkeeping problem. The more fundamental problem in the evolution of Monte Carlo equations is, again, the treatment of these high-density, high-temperature regions where the fluid and neutrinos are strongly coupled. This is kind of always the main problem in these simulations. The problem is that if you were just applying Monte Carlo straight up without any correction, you would need to handle millions of scattering events, emission and reabsorption of neutrinos during each time step for each packet, which would be very expensive. And on top of that, because of the stiff coupling with the fluid, you might again run into numerical instabilities in the evolution of your fluid if your time step is too large, which it nearly certainly will be if you don't do anything special. And so in spec, we have taken two separate corrections to handle these problems. The first is that in regions of high scattering capacity, we don't treat scatterings individually, but we just assume that the neutrinos follow the solution of the diffusion equation to determine where they end up at the end of the time step. And there are some technical difficulties here, which have to do with the fact that we do not have actually a covariant method to do this. But I think that from the test we have done so far, this is a pretty good approximation. I'm fairly confident that this does not introduce very large errors in our simulations at this point. The more difficult point is the treatment of high absorption regions, where neutrino would normally be continuously absorbed and re-emitted. There we do something that is a little bit more complex, which is called implicit Monte Carlo, which is a method where effectively you take part of the absorption capacity in your fluid and move it to scattering opacity. We can treat scattering fairly easily with the diffusion equation. In such a way that the sum of absorption and scattering opacity remains the same. That means that the diffusion timescale of your neutrinos through your system will remain the same. At the same time, you decrease the emission rate of neutrinos by the same fraction as the absorption rate, so that the equilibrium density of neutrinos remain the same. So you end up with a system of equation that is slightly different, but has the same equilibrium energy density and the same diffusion rate of neutrinos. What we have changed specifically is the time scale it takes for neutrinos to equilibrate with the fluid, which goes from a very, very short fraction of a time step, which is the cause of all of our problems, to something that is of the order of a few time steps for the choice that we made in spec. And that has the advantage of, one, limiting the number of interactions between neutrino and matter, and two, removing the stiff part of the equations by making your effectively interaction time scales a few time steps. We might wonder about how much of an effect this has on the solution, because yes, the equilibrium solution is the same, but we are not quite in equilibrium. And so we tested that actually for the type of profile that we have in neutron star merger simulations. This is a comparison between our approximate method for evolving neutrinos and the exact solution for a 1D profile, which is taken through the post-merger neutron star remnants of one of our simulation along the vertical axis, which is probably where the errors are the largest. And you can see that this is the log of the relative error, for example, in the luminosity. And in none of the neutrino species, it ever rises above 1%, which is much smaller than other sources of error in our simulations today. So currently, we are confident that at least on the short time scale that our simulation is evolving, this is not a major source of error. But this remains to be tested whether this method is valid at all. If you were to evolve for a much longer time scale, where diffusion of neutrinos through the neutron star might actually play an important role, and it is not entirely clear what kind of errors we are doing in that regime. All right. So to get to some results for Monte Carlo transport, the one thing that I wanted to actually show you here today is the difference between Monte Carlo results and the two-moment algorithm. And this is shown on this plot. Again, it's a vertical slice through a neutron-neutron star merger remnant, very similar to what I've shown you before. But no, what I'm showing in the color plot is the electron fraction of the matter. On the left with the Monte Carlo scheme, and on the right with the two-moment scheme. And you can see two things here, but basically that quantitatively, the impact of neutrinos in the Monte Carlo method and the two-moment method are fairly similar, with the increase in the electron fraction in the polar region and along the regions where matter is ejected along the disk, and fairly similar electron fraction in the disk itself. But quantitatively, there are obviously some noticeable differences, and it's probably easier to estimate those differences on the right, which is a histogram of the electron fraction for these outflows. And roughly speaking, you end up with 10% relative errors in the composition of your matter, and typically 10 to 20% errors in most of the other quantities that we have looked at. Right? So that's the kind of error then that we expect in the two-moment scheme with our best estimate of the energy spectrum of neutrinos. The errors are larger for other estimates of the energy spectrum when compared with Monte Carlo. And I should make a note here of the actual cost of these simulations. So this simulation here used about 100 million packets per neutrino species. And we use 3 species, electron neutrino, electron antineutrino, and then 1 species gathering all of the other neutrinos. And this leads to the Monte Carlo simulation taking about half of the computational time of our simulation. So not negligible, but also not an order of magnitude more expensive than doing pure fluid evolution, and actually quite comparable to the two-moment scheme with all of the bells and whistles and implicit time stepping that we were using in the other simulation. But this is actually kind of a worst-case scenario for Monte Carlo, and I wanted to briefly show this plot, which is from an ongoing simulation. And what we are doing now is doing Monte Carlo simulations of systems that do collapse to a black hole, or black hole neutron star system, which never have a neutron star remnant. And in this case, we can actually get away with doing Monte Carlo with a very small number of packets. Just about 1 million packets per species is sufficient for stable evolutions. And this is because now we have just have an accretion disk around the black hole, and there neutrino matter interactions are much slower. There aren't many regions with strong coupling between neutrinos and the matter, and effectively we just need to capture the long-term evolution of matter due to neutrino emission and possibly reabsorption, which doesn't require a large number of packets. We actually have less than 1 packet per grid cell in this simulation, and this still works. In this case, using Monte Carlo radiation transport in your simulation is actually cheaper than a moment scheme. And so when you have a black hole at the center rather than a neutron star, Monte Carlo becomes even more efficient. All right. So that's what I wanted to cover for Monte Carlo radiation transport. Now, I'm going to cover more briefly a couple of other topics, starting with the impact of R-process heating in the matter ejected by a merger. Now, this is something that's not always taken into account when we predict the properties of the outflows, but there are reasons to believe that when you eject matter from a neutron star merger, the energy released by the R-process can significantly impact its evolution. Because you are going to release about, if you start from neutron-rich outflow, maybe 8 MeV per nucleon. And a rough order of magnitude estimate will show you that if you start from marginally bound matter and you transform all of that energy into kinetic energy for the outflows, you are going to end up with outflows with a velocity of about 10% of the speed of light. So this is a significant change. But we also know that part of that energy, maybe about half, is lost to neutrinos. So it's actually practically a little less than that. And so we need to, when we make prediction for the asymptotic velocity of the outflow, or to try to determine which fluid elements are going to be eventually unbound in a simulation, we probably need to take that energy into account. And if we do a rough estimate, starting from a snapshot of a merger simulation, a few milliseconds past merger, and we try to determine how much matter is ejected and what its asymptotic velocity is, without taking the R process into account. This is from a neutron star merger simulation. We might end up with something like the blue curve. If we assign all of the heating to kinetic energy of the outflows, we end up with something like the red curve. And for our best estimate of how much of that energy is actually used to accelerate the outflows, or about half, we end up with the black curve here. And you can see that there is nearly a factor of 2 difference in the amount of mass ejected, as well as significant difference in the asymptotic velocity of the outflows, depending on whether you take that R process heating into account or not. And I want to emphasize that because this is actually, whether this is taken into account or not is sometimes an assumption that is partially hidden in the choice of equation of state that you are making and the choice of reference mass that you are taking for the nucleons in your equation of state. It can be difficult actually to determine which of those curves is actually used in a specific simulation. And considering the large differences between these different assumptions, I think it's very important to figure out which one we are using when we are actually predicting the asymptotic properties of outflow, and in the future to try to make sure that we actually properly take into account the amount of energy released by the R process in these outflows. That being said, these very simple estimates made a few milliseconds after the matter is ejected in merger simulations are probably not enough. And that is because effectively they assume that energy is deposited locally in a fluid patch, and that fluid patch evolves nearly independently of the rest of the fluid. This is not how fluid dynamics works. That patch is in contact with other parts of the fluid and may be impacted by other interactions such as pressure gradients in the fluid. And so what we did to estimate the impact of these effects with Siva Darba at Berkeley is to compare the predictions that we got a few milliseconds past merger with a full 3D simulation of the outflows continued for multiple weeks past merger. And this is shown in the same kind of plot here on the right, where the blue curve shows you what we predicted should be the velocity of the outflows without R process heating. Then the gray curve is the same matter here with R process heating included, but only using the information that we had at the end of the merger simulation, so without taking the long-term fluid evolution into account. And the fact that there is no matter here is an artifact of the method we have used here, which is to only consider the outflows within the blue curve here and not the marginally bound outflows that were at lower energy here. And then the purple curve here shows you the actual outcome of the 3D simulation, which you can see is significantly different from the local predictions made at the end of a merger simulation, showing you that non-local effects in the evolution of the fluid are going to be important in these kind of systems. And it is important not only for just the velocity of the outflows at infinity, but also for the general geometry of the outflow. Again, these are simulations by Siva, where you can see, long after merger, the distribution of the outflows in 3 different slices through the post-merger remnant. On the top, if you do not include any heating in the 3D simulation, and at the bottom, if you do include heating. The main result that we find is that the outflows are much more spherically symmetric in the presence of significant R-process heating. And the geometry of the outflows is much smoother, and that might lead to significant differences in the observable properties of the kilonovae powered by these outflows, and particularly differences in the angular dependence of the signal that we might get once we actually calculate light curves. So that's to show you that even though our process heating is often neglected when we actually try to predict the outcome, the evolution of the matter after a merger simulation, this is something that we should definitely pay attention to in the future if we want to make reliable light curve predictions for kilonovae. All right. The last topic I wanted to touch on is long-term, seconds-long post-merger simulations of black hole neutron star remnant, including non-ideal effects such as viscosity and diffusion. The motivation behind that is that we know that turbulence driven by magnetohydrodynamical instabilities, such as the MRI, are going to drive angular momentum transport and deposit heat in the post-merger remnant. We know that they are important in driving disk winds, potentially in leading to the collapse of a neutron star to a black hole. And in addition, and that is not generally taken into account in post-merger simulation, this turbulence should also lead to some mixing of the fluid and, as a result, diffusion of composition, entropy, and so on. Now, of course, the correct way to take this into account is to do full 3D simulations with magnetic fields that resolve the MRI in your simulations. And a few of those have been done now, but they remain extremely expensive, too expensive for large-scale parameter coverage in these post-merger systems. So if we don't want to do that, we have to rely on some sort of approximate method to capture the effects of the MRI. And one way to do that is to go to axisymmetric simulation and include subgrid viscosity or the largely simulations for the shear of your system in axisymmetric simulations of these post-merger remnant, as well as potentially some other transport effect that we can include. But this is not a perfect method, of course. There are a lot of physical processes that we know happen in 3D MHD simulations that these subgrid models do not capture. For example, they do not capture the early magnetically driven winds in simulations. They do not form relativistic jets because there is no formation of a large-scale magnetic field in these simulations. But what they do seem to give us is a reasonable agreement on the matter ejected on a relatively long time scale, viscous time scale, for at least the total amount of matter ejected in simulation. And they also give us a tool to study the impact of different physical processes on the post-merger remnant. And that's what we have been trying to do in spec. So what we include in spec, we use for the viscosity method that is very similar to the one developed by David Radice for merger simulations, the largely simulation method, where we effectively add to the ideal stress energy tensor of the fluid a shear tensor to mu nu here. The main difference with David's method is that we require that shear tensor to be orthogonal to the forward velocity of the fluid, which implies a small correction to the time and time-space component of that stress tensor compared to what David is using. Something that we found in our simulations at least was necessary to avoid some instabilities in some of our one-star test. In addition,
5 minutes left.
Yeah, okay, thank you, yeah. In addition to this shear tensor, we also add diffusion of the electron fraction and of the entropy. For the entropy, we use a heat flux here, which is proportional to the gradient of the entropy, and with a term that also depends on the gradient of the composition of the fluid. And then there are similar source terms for the evolution of the electron fraction, which also involves some mixing. Okay, these are only ways to qualitatively try to assess whether these effects might be important or not, because we actually do not have, at this point, a good calibration for the free parameters that go into these models, like the mixing length here, L used for the flux. And that means that we cannot make quantitative predictions at all, even if these models actually could have a certain parameter that matches the correct physics, which is not guaranteed. So this is just to know whether these effects are important or not and where they matter. So the last thing I wanted to show you were actually the results of the 2D simulations performed with spEC, with these extra physics. And this is a project led by Milad Haddadi at Washington State University in Matt Dewey's group. So he used spherical polar grids, as well as initial conditions taken from one of our black hole neutron star system for both the metric and the fluid, but axisymmetrized, of course. And then moment transport for the neutrinos. We chose the initial conditions to match an older simulation performed by Rodrigo Fernandez with Newtonian code, so that we could compare the effect of Newtonian physics versus general relativity. As in Rodrigo's simulations, our base choice for the equation of state was to use the Helmholtz equation of state, which includes alpha particles and protons and neutrons for the baryons. But we also have an option to instead use an extrapolation to low density of the DD2 equation of state, which also include heavier nuclei, assumed to be in nuclear statistical equilibrium. In some simulations, as we'll see, we will add that extra diffusion term for the composition and for the entropy. In some of them, we will also try to take into account our process heating, because again, these simulations are happening on seconds time scale, which is longer than the time scale over which the R process happens. And so we might actually have to take into account energy deposited by the R process. And we developed an approximate method to do that by continuously changing the electron fraction and removing energy due to neutron emission during the R process, which is kind of a way to approximate that out of nuclear statistical equilibrium evolution of the fluid during the R process. So a very approximate one. All right. So again, the initial data is used to match a Newtonian simulation by Rodrigo Fernandez, and then we have 4 simulations. One which matched the physics in Rodrigo's simulation with the Helmholtz equation of state and viscosity. One with the Helmholtz equation of state, viscosity, and those diffusion terms. And then 2 others that use the DD2 equation of state with heavier nuclei. One with just viscosity and one with viscosity and approximate R process heating, which allows us to look at the impact of all of those different physical processes. So the kind of takeaway here is that the total mass that we find in our simulation ejected is very similar to Newtonian simulation for the same input physics. But there was a higher velocity in all flows than in the Newtonian simulations. You can see the velocities here are about 7 to 9% of the speed of light, where it's more like 3 to 5% in the Newtonian simulations. And the outflows are accelerated actually quite far from the remnant. If we measure the outflows at only 10,000 kilometers from the remnant, the velocities were significantly lower. But maybe the most noticeable change is in the mass ejected by the system, where you can see that there are factors of 3 differences between the different choices for the physics included in your simulations. And in particular, whether you use the Helmholtz equation of state or the DD2 equation of state with higher nuclei has a very significant impact. And those diffusion terms have a non-negligible impact as well. So more visually, you can see the bound mass on in the simulations here is the top curve over time. The unbound mass are those curves rising over time here. And you can see that the simulations using the DD2 equation of state, the red and green ones, start ejecting matter earlier and then eject a lot more matter than the other ones. In terms of the composition of the outflows, ignoring the R process simulation, which actually predicts the composition at the end of the R process, which is different from the other simulation, which predicts the composition at the beginning of the R process, you can see that there is qualitative agreement on the average electron fraction of the outflows, but a simulation that does include mixing for the composition, not surprisingly predict a narrower band of electron fraction, which may be important for nucleosynthesis again. So this remains to be tested more carefully on a larger number of simulations. But, so that's what we have at the moment. So in summary, we have made some significant additions to specs, specifically on the microphysics side over the last few years. Monte Carlo simulation, largely simulation for both the viscosity and the diffusion, as well as changes to the low density equation of state. The Helmholtz equation of state is newly implemented in spec. We found that Monte Carlo simulations proved to be actually quite cost effective at the current accuracy of our numerical simulations. And have allowed us now to actually make estimates of the error in other approximate transport methods. We also find that our process heating in the outflows can be quite significant, both to determine the mass of the outflows, the velocity of the outflows, and their geometry. And finally, our recent 2D simulations show that the low density equation of state, the choices made for the low density equation of state, as well as non-ideal effects such as diffusion of composition and entropy, can be significant in these seconds-long post-merger simulations and might need to be included in the future. I'm going to stop here and take any questions that you might have.
Thanks a lot, Francois. That was a very nice talk. Yeah, let's open the floor up for questions. If you raise your hand, there's not too many. I can coordinate them, and if not, just speak up. And if there's none, I'm gonna ask something. All right, I don't see any hands, so let me ask. What is the energy and lepton number conservation with those Monte Carlo methods compared to other methods?
So it's not exact because it's not exact conservation because of the way we treat the coupling, which I don't really have the time to get into detail on, but it's not a huge drift in composition or I think compared to the numerical error that you are making just by finite resolution, the errors that you get in the YE evolution, for example, are negligible here. We do have methods that are actually such that on average the lepton number conservation and energy conservation is satisfied, but it's not satisfied for every single interaction between neutrinos and the matter.
Okay.
There might be some noise there, some more oscillations than your simulation that is purely conservative. But we haven't seen anything like a drift of the electron fraction or something like that, which in other attempts at doing transport using coupled Monte Carlo with a moment scheme, for example, that I tried in the past, was actually happening. There was problem with the conservation of electron fraction, leading to large errors in the simulations.
All right, thanks. So Zach had his hand up first. So Zach, take it away.
Really nice talk, Francois. Really a tour de force. Just wanted to ask if you could comment on the status of Spectre and how it's coming along and catching up to these efforts.
Right. So I'm not as involved in Spectre as in SPEC, but at the moment, Spectre can evolve binary black holes. As the MHD equations implemented, and it's currently being run for disks on a flat metric. I think the coupling between the fluid and the metric is in progress. We are starting to do things like implementing fancier equations of state and things like that in the code for the microphysics side. We haven't done neutron star measure simulations yet with Spectre because the coupling between matter and Einstein's equation is still a work in progress. So that's pretty close, I think, to being finished. Does that answer your question?
Yeah, no, thanks. And just a really quick follow-up. Is it, to what degree are the DG methods expected to be implemented in sort of, hydrodynamic coupling and whatnot? Is the plan to, when shocks arise, go back to finite volume or finite difference methods right now with Spectre? Just out of curiosity.
Yeah, pretty much, yeah. I mean, we have tried the standard, DG limiters, and we have tried going to finite volume or finite difference methods when when the solution becomes noisy, and the latter seems to work better so far. So at the moment, yes, that is what is happening. Is that in sharp regions, the code is going back to finite volume methods.
Thanks, Francois.
Okay, next up, Masaru.
So yeah, it's very nice talk, so Francois. So my question is about 2D simulation.
Mm-hmm.
So first question is how large is alpha parameter if you evaluate alpha parameter in your simulation?
I believe the alpha parameter was chosen. So it's not really an alpha parameter. It's that mixing length from David's method. But the mixing length was chosen, I believe, to match practically the alpha parameter in Rodriguez simulation, which I believe was 0.03. But I see Matt is here, so he might be able to answer that better than me. He's more involved. That's right, Matt?
Yes.
Okay, thanks.
And then so you said that so ejector mass is well, roughly speaking 10 to minus 2, less than 10 to minus 2 solar mass. So yeah. So then so how large is the initial disk mass? Disk mass is initially about 0.1 solar mass or something like that?
In this simulation, I think it's a little less than 0.1 solar mass.
So then so may I consider that about 10% of a disk mass is ejected as a outflow, so right? So
specifically from the viscous outflows in a disk, which I believe is fairly compact. So this is I think with Rodrigo, we have done some parameter space studies of how much mass is ejected as a function of disk parameter. And this is 5%, which is what you find here, was kind of on the low end. There was some more. So this is kind of on the low end of the mass ejection, I think. But it's consistent with the kind of results that Rodrigo was getting into at least for the same physics, using Helmholtz equation of state and viscosity and nothing else. It's consistent with Rodrigo's result. And so far these scalings with the disk compactness would still seem to work, but only one test. So it's hard to be sure of that. But also this does not include at all the earlier magnetically driven winds that you would expect if there is a strong large-scale colloidal field.
Yeah, if a magnetic field is amplified. So so in this so usually people perform a simulation with a very strong magnetic field. So it's not very physical. So it's not very clear the magnetic field impact is high one also. Yeah.
I agree. It's not clear at all. I mean, I was involved in the simulations with Sasha Tchaikovskaya, and in those, if you do start with a large magnetic field, you 20% of the disk ejected, but if you don't, the viscous component is actually the dominant one. And so I think at this point it's more like we don't know because it depends on the large scale structure of the field, which we can't resolve. So who knows?
Yeah, yes, thank you very much. Yeah.
Thanks.
Very nice talk. Yeah.
All right, next up is David.
Okay, thank you for the very nice talk. I have a question about the simulations of the ejecta long term. Maybe you said it, but I missed it. How did you implement R process heating in that case? In
this simulation, it's a simple heating source. Because it's all very neutron rich ejecta, so I think it's like it's a single function of time that heats the outflow because all of the ejecta kind of has very similar properties.
Okay, so for example, the formula I guess you used here.
Sorry?
I'm guessing that this means you used the formula from Korobkin et al. 2012, I think is the one that.
Maybe it might even have been something simpler, like constant over time for a second or something like that, which is actually a pretty good approximation to some of these things.
Okay.
I don't remember exactly because I didn't run these simulations. And then when we actually tried to move to compare to the predictions at early time in the spec simulations, we basically took the total amount of energy that was deposited in that model and assigned it to kinetic energy.
Okay, thank you.
I don't think, by the way, that the heating model that was here was just taken as an example of how much energy might be deposited over time. It's not a particularly accurate heating model in this case. So I'm not sure that it even goes to the level of detail of Korobkin.
Okay, no, but this answers my question. Thank you.
Okay, I guess we have time for one more question before we start setting up the next talk. So if anybody has another question, raise your hand, please. If not, I'm going to ask another question. Okay, no hands. So Francois, one question regarding the error between the Monte Carlo and the two-moment scheme. Apart from the costs, do you have any idea how that would change the relative errors if you were to do a spectral transport with the two-moment scheme?
Okay, so if I haven't done it, so it's wild guess, but my guess is that if you were doing a spectral moment transport, you would probably get a better agreement, a pretty good agreement on the electron fraction of the outflows, because most of the interactions occur pretty close. You can see that farther away there's not that much change. Occurs pretty close to the remnant. And in these regions, I don't think that things like the pressure closure has had much of a chance to have a huge impact. I might be wrong because that's just a wild guess on my part. But I see most of the error that is purely due to the closure in the moment scheme, the pressure closure, leads to large error in the. Can you see my cursor? Can you see my mouse?
Yes.
Okay, yeah. So in these regions here, you get some significant errors if we compare the energy density of neutrinos in the two-moment scheme and Monte Carlo scheme, which we have done in another paper. But not necessarily so much in these regions right above and right below the neutron stars, where most of those interactions occur. And so I would guess that you might get large errors in things like neutrino anti-neutrino annihilation in the polar regions, which could be important for things like jet production and things like that. But in terms of the composition of the outflows, which actually it's hard to see on this plot, but they are mostly moving along the edge of the disk here, at least in terms of where most of the mass is. I'm not convinced that these issue with the pressure closure would actually be significant. While the energy closure is definitely important, but that is just my guess because I haven't tried. And there are significant difficulties in doing energy-dependent M1 thing in merger simulations because of the large velocity gradients that we get compared to supernova simulations that create a lot of problems trying to define which frame you're actually going to use to define your energies of the neutrinos and beam them. And I think it's possible, but very non-trivial. I personally, that when I looked at it, I thought that it would be easier to do Monte Carlo by that point. But I think I would be very interested in seeing results with the spectral M1 because I think that would be a very valuable comparison if it can be done.
Okay, thanks a lot. So let's